All right. Welcome back to the interactive session of the course Discuss Fluid Flow. So we resume with what we left in the last week. So basically, if you remember, in the last week we tried to solve. So we tried to solve the flow field that would be generated by the motion of a sphere that basically moves with an arbitrary velocity u, and this u was something that we are supposed to find in the presence of a background parabolic flow whose velocity profile in the far field is basically known to us. Okay, so with respect to an axis which is fixed at the particle center, the far field velocity was basically known to us, with the exception that this u, which is the particle velocity, that basically is the velocity of this spherical particle, is unknown, and we said that we will use something which is known as the hydrodynamic force free condition. That is, the external force is being balanced by the drag force will inevitably give us what will be this u, and we will use that to eventually calculate what will be the particle velocity. So as I said, we use something which is known as the method of eigenfunction expansion. Although I explicitly did not solve this, we said that the equation for stream function, by taking a curl of the momentum equation, we said that the two equations, that is the momentum equation and the continuity equation, simplifies to a biharmonic equation involving the stream function of this sort, E4 psi equal to 0, whose solution can be found out by something which is known as the method of eigenfunction expansion, and its solution basically looks something like this. So as you can see, it's a series solution consisting of a function of r and a function of theta, and I said that this theta is now replaced as a new variable eta, which is basically cos of theta. So I said that eta is nothing but the cosine of theta, and these qn's are known as the Gegenberg polynomials, which are obtained from the Legendre polynomials. Okay, yeah, and they are related to the Legendre polynomials in this form. So I said that if psi satisfies this equation, then the solution of psi can be expressed in of this form given by equation 1. So all we need to do is we need to evaluate how many modes are responsible for this solution of psi for our problem, because this n start from 1 to infinity with the constants an, bn, cn and dn. Okay, so the objective is to find out these constants and the number of modes that are responsible for this solution of psi. Uh, and after that, once psi is known, we will use something which I repeatedly say is the hydrodynamic force free condition, which will basically give us the unknown u, which is the particle velocity in the z direction. Okay, so this is the idea, and we started this problem. So we started off by understanding the far field condition, that we know how the velocity field with respect to an axis that is fixed at the particle center would look like. So it was basically the far field velocity minus the particle velocity by using the concept of relative velocity. And then what we did is we transformed this uz into the, since we are dealing in axisymmetric spherical coordinates, we transform it into the r far field velocity and the theta far field velocity by using these relations. So these are basically geometric relations, as we saw. And then we also evaluate what u theta will basically look like. So once u theta is evaluated, we went on to evaluate the stream function psi of infinity, and we stopped at evaluating the stream function by simplifying it into some increasing power of eta. For instance, we rearrange the form of stream function into a function of r times eta power naught plus some function of r times eta squared and some function of r times eta power 4. Okay, so this basically is the idea that we saw. And then what I said is that this form of stream function can equivalently be written as some f function of r f1 times, in terms of the, so the idea is to write these forms in terms of the Gegenberg polynomials. The reason behind the reason behind doing this exercise is that this will now help us to identify which modes are present and which modes are absent. Okay, that's why we want to inevitably relate this form that we wrote here in terms of these Gegenberg modes, that is q1, q2, q3 and q4, and from here we will see that what modes will be present for different values of n and what modes will be absent. Okay, so this is something that so this is up to this we did it in the last week. we will begin by deriving or by understanding the solution from here on. But before that, if you have any doubts, you can ask me. I'll stop here for 1 or 2 minutes, or else we will proceed with the solution. All right. If there are no doubts, okay. So we will begin the solution of this psi. Okay, into writing something of this form. Okay, so the idea is we will write this expression in terms of q1, q2, q3 and q4, and if you do so, you can rearrange these terms. So the idea is you can rearrange these terms, okay, and can write psi infinity as something like this. So I have done the math, so I'll directly write that, but I hope the process is clear. It's just the rearrangement of the terms that you saw needs to be done. So psi infinity as a function of r comma eta can be written as, in terms of q1, q2, q3 and q4, these can be written as something like this: minus f1 by 2 plus f3 by 8, where f1, f3, these are all functions of r, as you have seen. So these are basically functions of r. So again I repeat, the exercise is to write these function of r and eta in terms of the Gegenberg, in terms of a function of r denoted by f1, f2, f3 and so on, and the Gegenberg polynomials qn's. Okay, so that's the idea. So this can be written as minus f1 by 2 plus f3 by 8, okay, plus you can write this as f, okay, f1 by 2 minus 3 f3 by 4, okay, times of eta squared, okay, plus f2 by 2 times eta cube minus f2 by 2 times eta plus 5 by 8 f3 eta power 4. Okay, so how did I get this step? This step, from this step, is that I have just expanded the values of q1. For instance, q1 is nothing but half of eta squared minus 1. Okay, so that's what I did, and I expanded that, and I expanded this uh, such that this comes of the form that we have written in psi infinity. Okay, so now if you compare, so for instance, if you compare the term associated with eta power 0, that is this term, because there is an eta power 0 here, this means that this f1 by 2 plus f3 by 8 will be equal to this term. Similarly, doing the same exercise in the same spirit, you can show that there is no eta power cube here, which means that f2 by 2 is 0, and similarly this goes on with f3 by this term. And if you go on and take more terms like f5r times q5, you can again prove that f5, f6 and f7 will be 0. This is because we have just compared this with the form of psi that we have manufactured out of the Farville condition. Okay, so now I will name this as equation 1, okay, and I would name this as equation 2. So the idea is, if you now compare, so comparing 1 and 2, okay, so if you now compare these two terms, what we will get is, you will get the first term, which is basically of eta power 0, as you can see. This term this term will be equal to this, which means I have what do I have? I have minus sorry. Okay, so as you have just joined, so I was just starting off with the solution. So from where we left, so basically what we did is we in the last class we evaluated, so we were basically solving the flow that would be generated by the motion of the sphere, which will now move with a velocity u. The velocity u is unknown to us, and this sphere was subjected to a background parabolic flow. Okay, and then we said that the problem is spherically symmetric, and we used the stream function approach, where we have said that the stream function satisfied the biharmonic equation. So in spherical coordinates, the biharmonic equation turned out to be E4 psi equal to 0, where E square is an operator, as we saw in the last. So the idea was that we saw that the solution to so I'll just quickly repeat. So the idea was that the solution to, I think it's here. Yeah, so the solution to uh, what is it, to this biharmonic form of E4 psi equal to 0 can be evaluated by using something which is known as the method of eigenfunction expansion. And although we did not explicitly show how this method is approached or method is done, we said that the solution comes out, the solution of psi, as we also might have seen in the week 6, I think, week 6 class, the solution of psi comes out in a series form which is something like this, where the terms in bracket are functions of R and Qns is the Gegenberg polynomial. Okay, so the idea is that if I know how many modes of size are there in the far field condition, and the constants an, bn, cn and dn, this is sufficient to give us the form of psi and all other variables that we seek to basically we seek to evaluate. For instance, if psi is known, we can go ahead and evaluate the velocity field, the stresses, and so long and so forth. Okay, so our first objective is to evaluate psi. The second objective is to enforce something which is known as the hydrodynamic force free condition, to give us the unknown velocity u with which the particle would basically move. Okay, so if you remember, our objective was also to evaluate this u basically by enforcing the fact that the net external force F external that the far field flow would exert on the particle is balanced by the drag force, which is F drag. And if these two are equal, then the particle would basically move with a constant velocity, which is this u, in of course in the z direction, since the problem is spherically axisymmetric. Okay, so this was the idea. So I was beginning to actually solve. So in the last class we basically solved so we said that the psi infinity, so we tried to write psi infinity as an increasing power of eta. So first term was basically some function of r times eta naught, then eta squared, and then eta power 4. Then what we said is that we now try to map this form of psi infinity into this form, which is written now in terms of the Gegenberg polynomial, because ultimately our first objective is to evaluate how many modes in that series solution is responsible for our solution. Okay, so that's why we wrote this basically. So psi infinity, we wrote this in terms of this some function of r times some function of this qns. Okay, then what we did is we expanded this q1, q2, q3 and q4. Okay, as I said, q1 for instance is nothing but half of eta squared minus 1, and that's why we just substituted half of eta square minus 1 in place of q1. Similarly, you can also find q2, since you know p2, that is, you know the second, so you know what is the second, what is basically the second mode of the legendary polynomials, and if you just integrate it from minus 1 to eta, okay, you can basically get q2, which is just a function of eta. Okay, so now then also, just like q1, if you find q2 and just substitute here, you can eventually show that these forms simply reduces to this form. Okay, now there might be one more question which says that why not take another mode f5 of r times q5 of eta. Okay, so you can take, but eventually when you compare this with this form, you will show that f5 simply reduces to 0. So what we were doing is we were trying to compare, after like expanding this q2, q1, q2, q3 and q4, we are now trying to compare equation 1 which we got from the far field psi infinity with this equation. Okay, so as I said, if we now compare the eta power 0 term, which means that this term is equal to this term. Okay, where I repeatedly said that this f1, f2, f3s are some function of r. Okay, so now if I compare, what I would get is that is the eta power 0 term. So let's say I'm comparing the eta power 0 terms. So the eta power 0 terms would give me what? It would give me minus f1 by 2, okay, plus f3 by 8, which is this term, okay, compared with this term, basically. So this should be equal to 1 minus u, okay, times r square by 2 minus r power 4 by 4, okay. Similarly, if I now compare, okay, the eta squared term, okay, because there is this eta squared term. So if I now compare the eta squared term, what do we get? So the eta squared term, if we compare, basically we get this, that f1 by 2, so this term is equal to this term, which means what? Let's see this. So it is, I think this is f1 by 2, okay. Yeah, so just 1 second. Yeah, so this is f1 by 2, okay, minus 3f3 by 4. Okay, this becomes equal to the, so the eta squared term in the form of psi infinity is basically something like this, which is r power 4 by 2. Okay, let's write this. This is r power 4 by 2 minus 1 minus u into r by 2. Okay, and that's it. All right. So far so good. Similarly, if I compare the terms with eta power 4, this means that f4 is basically, so eta power 4 is basically this, which means that minus r power 4 by 4 is basically f5 by 8 f3. Okay, let's do that also and see. So if I compare now the eta power 4 terms, it becomes minus r power 4 by 4. Okay. This becomes equal to, so minus r power 4 by 4, this will become equal to what? This will become equal to 5 by 8 f3. Okay, so this will become equal to 5 by 8 f3. All right, let me check if I did everything correct or not. Yeah, I think I did it correct. All right, so now tell me if you have understood what we did, what will be this term equal to, what will be this f2 by 2 equal to, if I compare eta power 3.
0.
Yeah, exactly. This should be 0. That is simply because we do not have any eta cube terms here in this form of psi. Okay, and that's why this term f3, that this term basically f2 by 2 will turn out to be 0. Okay, 2 by 2, this should turn out to be 0. All right, which means you can also, so this means this term would basically come out to be 0. And this also means that this term will also go out to be 0. Okay, so all we need is to solve three equations uh, embedded in the terms of eta power 0, eta square, and eta power 4, in terms of this f1, f3, and what, and so yeah, so how many equations do we have basically? uh, Hold on. Did I do anything mistake here? Just 1 second. I'm just cross checking with my notes. Just 1 second. One. All right. So what we now need to do is we now need to evaluate this f1 and f3 basically. So we now need to evaluate this f1 and f3. Okay, from these available equations, one is this. Okay, one is this, which is this equation. Just 1 second. Just 1 second. I'm just cross checking something with my notes. Just a minute. 1 by 2 plus 3 by 8. That is to go to this term and all right, let's do it. Let's do it and see what we get. If there is mistake, we will just We will try to find it from there and there. So from this term, so from here, so the objective is to evaluate this F1 and F3. Okay, that's all we need to do, F1 and F3, because we know that this F2 is basically 0 from comparing. F4, I think, yeah. So do we need F4 here? Hold on. I think there is one more term. Yeah. Okay, this should be F4. Okay, I think I did some that's one. Okay, that's good. All right. So I think the comparison is done correctly, right? This term is basically equal to this. This is equal to this, and this term minus r power 4 by 4. This is equal to 5 by 3 f3. Okay. So far it appears to be good. Let's proceed. If there is mistake, we'll just find it out. So by comparing this term, that is the coefficients of eta power 4, what we can conclude is that from here I can write that f3 is basically equals to what? So f3, this should be 2. Okay, and f3 becomes equal to minus 2 by 5 r power 4. Okay. So from just by comparing this, just by evaluating this term, we can say that f3 is minus 2 by 5 r power 4. Okay. And let's now use this. Okay. We have two equations, but what I see is this equation and this equation is what? Is this multiplied by this r power 4 by 4, and there is this. So although we have two equations, maybe let's substitute this here. So I think we'll end up getting the same value for f1 by substituting f3 in either of the two equations. Okay, let's try to check. Okay, let's try to check. So what we will do is we will now try to substitute f3. Okay, we will now try to substitute f3 in, let's say, here in this equation, and let's see what do we get. So if we substitute there, it will be what? It will be minus f1 by 2 plus it is f3 by 8. Okay, so this would become minus 1 by 20, I think. Just check it out. So f3 by 8 would be what? F3 by 8 would be 5 into 8. Okay, this would be 40, and so it would become minus 1 by 20. Okay, looks good. So minus f1 by 2 minus 1 by 20 r power 4, okay, is equal to, this is equal to what? Is equal to 1 minus u, okay, times r squared by 2 minus r power 4 by 4. Okay. All right. So now what we will do is, maybe we can simplify this. We can multiply by 2 on all sides. So then this term would become minus f1. So objective is to find f1. I hope you can understand that. So it will be f1 minus 1 by 10 r power 4, that is equal to 1 minus u times r squared, okay, minus r squared by 2. So this means your f1 basically comes out to be what? And let's do one more step. Let's multiply the whole equation by minus 1, which means I have something like this. F1 to be equal to r squared plus r squared by 2 minus, this will be plus, so this will be minus r power 4 by 10. Okay. And if we just simplify it, f1 is basically equal to u minus 1 times r squared plus, this would be what? This should be, if I'm not wrong, this should be 10, this would be 5 minus 1 is 4. So I think this would be what? Be 2 by 5. I mean 4 by 10 r power hold on. Just one again. Did I do any mistake here? Like minus f1. Just one second. I'm just checking one down. So it's minus f1 by 2 and f3 is minus 2 by 5 r power 4. Just 1 second. 2 by 5 r power 4. So we just substituted it here. So it is f3 by 8. So it becomes 1 by 20. Just 1 second. It becomes 1 by 20 r power 4. Uh, and this becomes 1 by 20 r power 4. I think this is correct because it is f3 by 8. Okay. So this becomes 40 1 by 20 r power 4. This looks correct. And then I'm equating with this term. Okay, this should be r power 4. Okay. This is r power 4, which is correct. Okay. I think. Uh, and then what we did is this is this. And f1, and then I think we multiplied by 2. So I think we wrote, so this is wrong, right? Because we just multiplied by 2, so this would be r power 4 only, right? This would be r power 4 only. Yeah. Okay, this is fine now. Okay, and then this would become what? This would become r power 4 only, which is fine. And then this would become 4 by 10 into r power 4, which means it becomes 2 by 5. I think this is correct. Please check it out. So do the math by yourself also. So f1 in terms of r basically comes out to be 1 minus u minus 1 times r squared. Okay. Hold on. Yeah, so it becomes u minus 1 times r squared plus 2 by 5 r power 4. Okay. Can you quickly check it out? So this is your f1. So we are done evaluating the f3 and f1 that we require to do. Okay. So you can quickly check it out that if you substitute what I was saying is that if you substitute this f3 instead of substituting it here, if you substitute it here also, you will get the same f1. Okay, you can check it out by yourself. That is, instead of
Yes,
substituting,
yes.
yeah, you'll get the same f1, right? You should get the same f1 because you are just comparing terms here. Okay, so the f1 that you get from there also will be the same. So which means that we are now done evaluating this f1 and f3. Okay, so f3 is basically this and f1 is this, which means now can you tell me that which modes of n, so it is evident now that which modes of this summation, where it is, where is the, yeah, so which modes of this term are present now. So it's evident that we just have n equal to 1 and n equal to 3 modes, right? All other modes with respect to the far field stream function will vanish basically. So the reason behind this is that although this psi denotes the complete solution, psi should always approach its solution in the far field. Okay, so it's not like that the actual psi, which is basically the disturbance part and the far field part, will not have any other modes apart from the modes which are there in the far field, because the disturbance psi, so the objective is that this psi is the total stream function that we are trying to solve for. You can always write this psi as psi disturbance, which is due to the particle, and psi far field. Okay, so the idea is that this psi disturbance will always go to 0, which means that your psi, that is the total stream function, should always approach to the far field stream function that we already have from the velocity boundary conditions. Okay, at the far field, which means that based on the fact that we now have only two values of f1, that is f1 and f3, and all other modes are 0, so we can rest assured, we can just write that uh, so we can, so let's, before writing, let's write now psi infinity. So psi infinity can be written as what? So psi infinity can be written as f1 times of r times q1 of eta, if you remember, plus f3 times of r times q3 of eta. Okay, and if you substitute this, if you substitute the values of f1 and f3, f1 is what? F1 is basically this, which is so f1 is like, so I write something like this: 2 by 5 r power 4 minus 1 minus u, I can write it like that, into r squared. Okay, times what? Times q1 of eta, plus I have f3. F3 is what? F3 is minus 2 by 5 r power 4. Okay, so this should become minus 2 by 5 r power 4 times q3 of eta. Okay, so we have now successfully found out what will be the far field stream function in terms of the Gegenbaur modes. Okay, so these are known as the Gegenbaur modes, the various values of n's that we get. Okay, so we have found out the far field stream function in terms of this Gegenbaur mode. So as I said, the solution of stream function satisfying E4 psi equal to 0 will have exactly the same number of modes as the far field as that of the far field stream function. The reason behind is that the disturbance stream function will always go to 0, which means that the solution, the series solution that I just now showed, will have two modes. That's something that I will write. The series solution will have two modes. So the individual values of n are known as modes. Okay, so I think you guys know about this. So the series solution will have two modes, and what are these modes? So one value will be n equal to 1, okay, corresponding to q1, and the other value would be n equal to 3. So this means that the series solution of stream function, that is the solution we are trying to seek, of psi as a function of, let's say, r and eta. I will just now write this. For the sake of clarity. So our series solution was something like this. It was n equal to 1 to infinity. Okay, it was an times r power n plus 3 plus bn times r power n plus 1. Okay, plus cn times r power 2 minus n plus bn times r power minus n multiplied by qn of eta. Okay, so now it can be easily seen that comparing this tree with the series solution, I know that only n equal to 1 and the third mode survives. Okay, so this is the most important step in evaluating the solution of this series solution. Okay, trying to see which modes actually survives in the complete solution of the stream function by looking into the far field solution of its counterpart. Okay, all right. So if this is clear, can you now tell me? Okay, so what are the next step? So can you tell me what are the next step? So the next step, yeah, go on.
Get this in,
Yeah, exactly. So do you mean so we need to get these
in
constants a n, b n,
yeah,
c n, and d n? Yeah, exactly.
coefficients. Yeah.
Yeah, exactly. So the next step now is to get the constant a n. Just 1 second. My laptop is actually not in charge. I'll quickly give it to charge. Just 1 second. Yeah, sorry for the interruption. So the next step now is to evaluate these constants a n, b n, c n, and d n's. Uh, we'll do that. But by the way, I would like to say that I have tried to communicate with the associated individuals who actually frame the assignment answers, and I have tried to communicate with them. So I'm just waiting for their reply. I have said that like the questions which we discussed. So I think 2 or 3 questions answer key has already been updated. I think that was for assignment 5, if I'm not wrong. Can you clarify on that?
Okay, okay, I didn't check. I will check.
Okay, yeah, sure. So I think assignment 5, the doubts were mainly on assignment 5. So I think 2, 3 answers were updated. The rest they're trying to check. So there is a separate set of individuals who prepare the assignment key and the assignments. So I have also reported them about the question 2 of assignment 7, that the boundary layer questions, and let's see what the response comes out. But if it's wrong, and which we assume that it's wrong, the correct answer is wrong basically, they will update it accordingly. All right. All right.
Thank you.
Okay. Yeah, sure. Okay. The next step now is, as you have said, is to evaluate these constants a n, b n, c n, and d n's. And now again, the logic is that the constants an and bn is can be evaluated from the form of the far field stream function, and while the constants cns and dns, okay, these will be evaluated by applying the boundary condition on the surface of the sphere. We will shortly see how systematically it is done, but before that, before evaluating these cns and dns, let us now try to evaluate a priori what these constants an and bn will look like. See, the logic is simple. Why these ans and bns come from the boundary condition far field? That is simply because, since see, these modes of n are always a positive integer. Okay, n can never be negative. Okay, which means that it's the n's at the far field that dictate these ans and bns. Okay, we will see that shortly. I mean, things should be more clarified once we try to evaluate this. So now, can you tell me, by looking at this form, by looking at this form, okay, this and this form, then can so so the idea is, by looking at equation 3, okay, is this mode possible or not? Can you tell me, is this, I mean, not mode, I would say, hold on. Yeah, so I am just asking, is a non-zero A5 possible or not? That's what I'm asking by looking at this equation, that is equation 3. See, try to understand the coefficient of an, and try to compare this coefficient with the existing coefficient that we have, and try to answer, is a non-zero A5 possible or not, or a non-zero A4 possible or not? That's what I'm asking. Okay, because see, n always varies from 1. Okay, so I can have an a power 4 a1 plus this is a sorry this is so if I put n equal to 1, it should be what? It should be a1 times r power 4. Okay, I mean, I wrote it wrongly. Sorry for that. This should be 2 basically, and this should be 1. Okay. Let's write some coefficients and then I'll make you understand. Okay. So the idea is, if we now expand these values of n, okay, let's say I expand it from n equal to 1, n equal to 2, n equal to 3 into this term, okay, and try to map it with the functional form of r that we have, okay, the highest functional form of r in the far field solution. So in that spirit, can you tell me, if I put n equal to 2 here, this would be what? This would be a2 times r power 5. Okay, so is that possible by looking into the solution of psi infinity given by equation 3? Can you tell me?
No.
Yeah,
Zero in the
yeah,
A part
exactly, exactly, exactly. Which means, so what I am trying to say is that ans, okay, what I am trying to say is the ans that we have, the ans that we have will only have one form, which is just a1, okay, and that would be, and can you tell me what will be a1 by comparing? Can you tell me, okay, what would be a1 by comparing this and this? It's just simple, right? It's just 2 by 5.
two by 5.
2 by 5, exactly. So a1 will basically be equal to 2 by 5. That is just by comparison. Okay, that is just by direct comparison. And so for all the ans, a1 is just 2 by 5, and this is not equal to 0. And I can safely now write that all ans for n greater than 1, okay, or I can write something like this. So ans equal to 0 for all n not equal to 1. Okay, that means if I pick n equal to 2, that means a2, and then I pick n equal to 3 and so on and so forth, all these coefficients has to be equal to 0. This is again attributed to the fact that the far field stream function basically satisfies this form. Okay, so that's the logic. That's the logic that, as you rightly pointed out. So this means that, so what I now have, this is that I have safely evaluated the ans. So what we did, we evaluated that there can be two modes of n that is possible. Okay, which means n equal to 1 and n equal to 3. Okay, and from that also, I only know that a1 is going to be equal to 2 by 5 and a3. So since we know that now there is only three modes, okay, sorry, two modes, n equal to 1 and n equal to 3, this a3 has to be equal to 0. Is this clear or not? With a1 equal to 2 by 5. So is this clear or not? Like, I hope this is clear.
Yes.
Okay. Similarly, in the same spirit, can you tell me, in the same spirit, can you tell me what will be the values of B1 and B3, basically?
B1 will be minus 1 minus u r square,
Yes, exactly.
and
Uh,
B3 will be minus 2 by 4
R
r.
won't come, right? Because these are just constants, right? I think R
Yeah, yeah.
won't come. It will, so
Yes, yes,
B1,
sorry.
yeah, B1 will be just U minus 1, and B3 again will be just minus 2 by 5. Okay, that is
Minus 2
this
by
term.
5.
Yeah, exactly. Good. So B1 will be just, as you said, B1 is just U minus 1, and B3 is just minus 2 by 5. And this actually matches with my notes as well. So this means we are doing it correctly. So that's it. That's it, guys. We have evaluated the two form of constants, ans and bns. Okay. Again, I would repeat, how did we do this? So we'll do, so it's a very systematic and a very nice approach without using, basically we did not, so although we need to use something which is known as the orthogonality principle here, without using the orthogonality principle yet, so it's like we have used the orthogonality principle without using the orthogonality principle. It's something like this. Okay, this was possible because we could write this, so we could write the form of psi infinity as this form. Okay, as basically this form, and then evaluating this f1, f2, f3, and f4. Had this not been possible, we had to use a generalized concept which is known as the orthogonality principle of Gegenbaur polynomials. Okay, you can look into that. So it's very simple. It's just like the orthogonality principle of sine and cos. It's just also like the orthogonality principle of Gegenbaur, which means that it's something like this. So if you integrate qn of eta with qm of eta, and you integrate this from minus 1 to, let's say, 1 d eta, then if n is not equal to m, this integration eventually turns out to be 0, and if n is equal to n, it goes into some constants. Okay, so that's the orthogonality principle. You can similarly find out using the orthogonality principle that how this a1 and a3 and b1 and b3 look like. But without using that also, since we are able to write the form of stream function as an increasing power of eta, okay, we found out what these constants f1 and f3 would be like, how this constant f1 and f3 as a function of r would be like, and then using the fact that the far field stream function has only two modes, n equal to 1 and n equal to 3, comparing that with the form of stream function at infinity, we found out what these constants a1 and a3 and b1 and b3 would look like. I think you guys are clear up to this point. Okay.
One doubt only.
Yeah.
Coming of equation second, can you explain once
Yeah,
more?
sure. Equation second is what? Equation second is this, right? This is equation second, right?
Yeah.
Yeah, okay. I'll explain that. I'll be happy to explain that. No worries. So yeah, so what we did is, see, this equation is clear to you, right? How did we write this equation? It's clear, right?
Yes, yes,
Yeah. So
yes.
now the objective is we want to write this equation into this form. Okay, we want to map it's not right. We want to map this equation into this form. Okay, into this blue form. Okay. So for that, for that, what we did is we wrote a generalized expression of sine infinity as some fn of r times qn of eta. Okay, where n varies from 1 to 3 up to infinity, let's say, and that's what I have written it down here. Okay, and then what we did is we expanded this q1, q2, q3, and q4, because see, this q1, q2, q3, and q4 are just Gegenbaur polynomials, right? They are known to us. For instance, in last class I showed you that, in last class where it is, in last class I showed you that q1 is basically integration minus 1 to eta is eta d eta. Okay, which means q1 is nothing but half of eta square minus 1. Similarly, if you know p2 of eta, that is the second mode of the legendary, if you know p2 of eta, by using this you can directly calculate q2 of eta, which will be some functional form similar to this. Maybe it will have some higher higher power of eta, but it will be similar to this. So what we did is we just substituted the value of q1, the value of q2, the value of q3, and q4. Okay, for instance, I just substituted q1 as half of eta square minus 1. Okay, for instance, I have the value of q2. Just hang on, I'll show you how q2 looks like. Just wait a second. Oh, I think I have that. Just one second. Yeah, I think I have this here. Okay, hold on. So I'll show it here. So for instance, Q2 is basically half of eta cube minus eta. Okay, because you can show that P2, you can see in the net that n equal to 2 mode of the Legend ray is basically this. It is half of 3 eta square minus 1. Oops, sorry. It is half of 3 eta square minus 1, which means if you do this thing, integration from minus 1 to eta, P2 of eta, d eta, you eventually get something like this. You can check it out that you will get, you are bound to get this. Similarly, Q3 is this, okay, 1 by 8 5 of eta squared minus 1 times eta squared minus 1. Okay, this is Q3. This is Q3 and this is Q2. So what we did is we just substituted this Q1, Q2, Q3 in this equation, basically. For instance, I substituted Q2 as this term, as you just saw. So Q2 is basically half of eta cube minus eta. And once I substituted it, I just rearrange this equation in an increasing power of eta. For instance, in an increasing power of eta naught, eta squared, eta cube, and eta power 4. Okay, and then once I do this, I just compare this equation 2 with equation 1, basically. Is this clear or not? Like, how did we get that?
Yeah, only like
Yeah.
Q3, Q4, Q5 terms will be having eta power
Eta
greater
power
than 4.
greater, yeah, which are essentially absent in the psi infinity term, and that's why they will, even if you write, they will just, so the coefficient, let's say f5 would be just 0 by comparing with the fact that we don't have the higher powers of eta in psi infinity term. Okay, so it's like if you have a very complicated flow, complicated far field flow, not a parabolic flow. Let's say you have a flow which have, let's say, the power of r as r power 7. Okay, we can have a flow something like that. Okay, the nature, so parabolic flow is basically what, it's just r squared. So then, so you have terms in the vicinity of r power 2. For instance, if you have a term which is much more complicated than that, if you have a background flow which may have some terms like eta power 6 or eta power 5, then you have to go to the higher modes, let's say up to, let's say, n equal to 3, n equal to 4, or n equal to 5, and so on and so forth. Is this clear enough?
Yeah,
Yeah,
thank
okay.
you.
So yeah, sure. So that's the idea by how we calculated that. Okay. Thank you for the question. All right. I'll just wrap this because just break the continuity. Yeah. So we are almost there, guys. So basically, what we did is we we just express the solution of psi infinity in this form, and now we have we have also evaluated. So what we did is we have also evaluated this a1, a3, b1, and b3. Okay, all we now need to do is we just now need to evaluate this c1 and c3 and d1 and d3. Okay, and after that I will show you two approaches. One is through a theorem which is very powerful. The theorem says that if we want to evaluate the drag force, okay, it is sufficient to evaluate just this constant c1. Okay, and if you know c1, by using a theorem we can directly say what will be the drag force. Okay, the other way is a more traditional and a more orthodox way, is that you evaluate all this constant. Okay, we will see that orthodox way, or what the longer way, we'll see that shortly. But yeah, let's first evaluate the constant c1, c3, and d1, d3. Okay. All right. So before that, what I will do is I will first write. See, this is in summation form, right? I will just first write this entire equation now, since we know that there is just going to be two modes, n equal to 1 and n equal to 3. I would now write this form into just in terms of just two modes, and the 1th mode and the 3rd mode. Okay. So what I mean to say is something like this. Okay. I will just write psi to be something like this. So it is just 2 by 5. Okay. R power 4 plus u minus 1 times r squared plus c1r plus d1 by r okay, times q1 of eta plus minus 2 by 5, okay, r power 4 plus c3r plus d3 by r into q3 of eta. So can you understand what I basically did here? So it's now that it's very simple. It's now that I know just n equal to 1 and n equal to 3 survives, and also I know what are the values of a1, a3 and b1, b3. I just substituted that in this equation. That's it. For instance, if n is equal to 1, the c1, this would become c1 times r power 1, and that's why we have written this term. Okay, and that's why we have written this term. Okay, and for instance, if there is and so for instance, if there is n equal to, let's say, 1, this term would become just r power minus 1. Okay, I hope this is clear. Yeah, just checking that did I do this correctly or not. So it's 2 by 5 r power 4, this is fine. So a1 is this, and this is r power 4. b1 is something like this with an r squared, because it is n equal to 1. And then what do I have? I have this term with q1, and for what do we have? Yeah. For n equal to 3, basically, for n equal to 3, okay, I think I did some mistake. Let's see, for n equal to 3, if I write, okay, so this term, so this is just 0, uh, and then this term is the coefficient of bn. So coefficient of bn is what? Coefficient of bn means b3 is minus 2 by 5, which is basically this term. Okay, this should be minus 1, right? This should be minus 1, I think, because for n equal to 3, this would be 2 minus 3, which means this is r power minus 1, and this would be just minus 3. So it is d3 times, yeah, I think this should be this. So I think this is correct, right? Can you just quickly check? I think this is
Yes,
fine.
yes.
Yeah, so I'll just write this down as something like this. It would be c3 by r, basically something like this. It's just that we are substituting n equal to 3 here. Okay, all right. So what we now have, as you can see, what we now have is just, we are just left to evaluate this c1, d1, c3 and d3. Okay, and how do we do that? Can you tell me, or can you just give me a suggestion? How do we do that? So we have not used one more thing, basically two more things.
No slip conditions.
Yeah, no slip, and no slip is what, no slip will give us u theta at no slip is what, u theta, the theta velocity, the tangential velocity at r equal to 1 is 0, and one more thing we need, right? Can you think of one more condition that should be there?
Axis symmetry.
Axis symmetry is okay. Axis symmetry means that if you differentiate u theta with respect to theta, okay, that is 0. But yeah, you can use that. There is one more condition, which is the no penetration condition, right? That u r at r equal to 1 should also be equal to 0, right? Since the sphere is solid, flow cannot penetrate the
Yeah,
boundary of the sphere, right? So we will see u theta difference with respect to theta. This will basically be a little bit complicated. So we can use the simpler thing, that is the no penetration boundary condition and the no slip boundary condition. Okay, and we will use that basically. So the first boundary condition, but before that I will just write that c1 and c3 or oblique c3 and d1 and d3, this will be obtained by applying boundary condition on the sphere. Okay, all right. So now if I apply the no penetration boundary condition, it gives us what? It gives us that ur, that is the radial velocity at r equal to 1 is 0. And if you write the radial velocity in terms of the stream function, you can directly write that del psi by del eta. Okay, you can just check it out, the math, at r equal to 1 is 0. Okay, which means what? Which means what do we have? Which means that you just need to apply this, okay, at r equal to 1. All right, just 1 second. So yeah, so what do we get? Basically, you just need to apply this. So you just need to use this and apply the fact that del psi by del eta, okay, del psi by del eta at r equal to 1 is 0. So if you apply this, what do we get? Let's see. Let's see what we get. Just 1 second. I'll just yeah. I think we are on the right track. Anyway, let's just apply this. So when you do this for r equal to 1, what do we get? Okay, let's see. It is 2 by 5. Okay. We are evaluating this at r equal to 1, which means 2 by 5 plus u minus 1 plus c1 plus d1. See, this is just a function of r, so it will come out of the integral, which means I have just d of q1 by d eta. Okay, I hope you are with me on this, and this should be minus 2 by 5, okay, plus c3 plus d3, okay, times d of q3 by d eta equal to 0. All right. Okay. So what now do we have? Okay. So I hope this is correct. All right, we will see, but I hope the math is correct. Okay, so now can you tell me that from the first boundary condition, okay, so this is the first boundary condition. This is the first boundary condition. And from the first boundary condition, I got that. What? So, by the way, can you tell me what is this? In terms of some other known polynomials, can you, I mean, q1 is also known, but a simpler polynomial. Can you tell me what is this? See, the hint is if this if this is q,
Eta.
yeah, exactly. But like, yeah, this is eta. In fact, this is p1 of eta, right? That's what you are saying, right?
Yeah.
Yeah, exactly. So which means this is just p1. That's what you are saying, right?
Yes. Yes.
And this is p3, correct?
P3.
Yeah,
Yes.
exactly. So this means that these are just the Legendre. So always remember the integration of Legendre's Gegenbehr and the derivative of Gegenbehr with respect to, of course, eta is always Legendre. It's always the other way around. Okay, it's just the integration and the differentiation concept. So the thing is, that's not what I intend to say. The thing is, like, if we now have a function of eta multiplied by some constant plus another function of eta, okay, multiplied by some constant, and this is equal to 0, can you individually say, so this can only be 0 if this can only be 0 if this entire term is 0 and this entire term is 0 individually. Like, do you agree with me on this or not?
Yeah, because they're independent bases.
Exactly, exactly. They are independent. So that's exactly the word. They are independent basis basically. So this means that all the individual modes of whether the Legendre, okay, and or the Gegenbehr, they are mutually independent with one another. Okay, you cannot express, and that's why they satisfy the orthogonality principle. That's precisely the reason. Okay, this means that you cannot write one mode of Gegenbehr in terms of all other modes. Okay, that's basically the term that you say that they are orthogonal. They are mutually independent. That's another way of saying that. Okay, which means I can now write 2 by 5 plus u minus 1 plus c1 plus d1 equal to 0. Okay, and what? And c3 plus d3 equal to 0. Okay, let's name this as some, what do we name? Which equation do we have? Okay, let's name it as some equation 4a, and let's name it as some equation 4b, basically. All right. Next, if we use one more condition, so we are just left with one more condition. If we use u theta if we use the fact that we use the no slip boundary condition, which means u theta at r equal to 1, which is basically the no slip. Okay, if we use this, you can also just use the relationship between u and psi in spherical coordinate. You can show that u theta can be written as del psi by del r. Okay, at r equal to 1 and this is 0. And if you do this, what you need to do is you just need to basically find the del psi by del r from here. Okay, you just need to do this. Let's try to get what is del psi by del r. So first term is what? It will be, so let's do this. So the first term, if I evaluate del psi by del r, would be what? It would be 8 by 5 r cube. Okay, just write this. Uh, let's evaluate this. So it would be what? It would be 8 by 5. Just check the math because I just need to scroll up and down continuously. It is 8 by 5 r cube plus the second term is what? The second term is 2 times of u minus 1 r. Okay, 2 times of u minus 1 times r. Okay, the third term is what? The third term is just c1 and the fourth term is minus d1 by r square. The third term is c1 and the fourth term is minus d1 by r squared to be precise. And the outside term is basically q1 of eta. Okay. Similarly, if I apply the same, so if we do the same exercise in the third mode, what you will get is this term would be minus, what is this? Minus 8 by 5 r cube, I think. Minus 8 by 5 r cube. Okay. I think I'm not wrong. Minus 8 by 5 r cube minus 3 by r squared, and this would be what? This would be minus 3 d3 by r power 4. I think that's it. Minus 3 d3 by r power 4. All right. And this is q3 of eta and this is equal to 0. And using the same logic that you said, and of course we are evaluating this at r equal to 1, which means this is just 1 and this is just 1, this is just 1, this is just 1 and this is 1 with this is 1. So if you just apply the same logic as you say that since these two are mutually, like you can these two are mutually independent, you can simply write that a by 5 plus 2 into u minus 1, okay, plus c1 minus d1 is equal to 0 and minus a by 5, okay, minus c3, okay, minus 3d3 is equal to 0. All right. So this means we just end up, I would name this equation as 4c and 4d. So this means we have, so all that things that we did, we are now just left to solve for four constants c1, c3, d1, d3, and this is sufficient to give us the entire solution of the stream function. Okay, so it's now very simple because we have now four algebraic equation and four unknowns basically. So our unknowns are c1 d1, c3 d3, and of course we also have c1 d1 and c3 and d3 in these equations, and we have four unknowns and four equations. So I will not do the math here. You can do it from yourself, but I will I will, so at this point of time I will straight away like uh, write a particular theorem which is very essential, and this actually eases our subsequent calculation. Okay, and I will tell you why, but before that, just 1 second. So the theorem goes something like this, and you can find this theorem in the book of so I mentioned a book maybe in the last class that was by the book. So the name of the book is Advanced Transport Phenomena by Professor L. Gary Leal. It's a Cambridge University publication. So you can find this theorem in chapter 7 of that book. Uh, and the theorem says, okay, the theorem says something like this. I'll pinpointedly write the theorem because it's very important. So it is something like this, okay. So the theorem says for any problem, okay, with psi as a function of r and eta expressed as, so if you express, so what it says that if you are able to express psi as this form, okay, as this form, that is this series solution. I think this is given by equation 1, so I'll write it as equation 1 expressed as equation 1. So remember, equation 1 was that series solution of psi, that general series solution of psi that one get by using eigenfunction x function. Okay, so if you, for any problem with psi, if you can express that as 1, the force exerted by the fluid on an arbitrary axisymmetric body with its center of mass at mod x equal to 0, which means your basically your axis center is basically your center of mass. That's what it is saying. Is so it says that the force that the fluid essentially exerts on any arbitrary axisymmetric body is something like this. It is Fz, where Z denotes the axis of symmetry, is basically 4 pi mu uc lc times c1, where that c1 is that c1 what we essentially calculate, that modes of c1 d1 c3 d3, that n equal to 1 mode of that coefficient c1. Okay, that's what I was meaning by c1 here. All right, where remember this z that you see here, this denote the axis of symmetry. Okay, so what does this theorem means? So it says that, say, this theorem, I don't know if you can appreciate it or not, it's very powerful. What it says is that if, let alone be a sphere, okay, if you have any body, if you have any arbitrary body, but the essential condition is that it should be axisymmetric about an axis. Okay, let's say this body is axisymmetric about the z axis. Okay, then when there, so then if under any circumstances either a fluid moves past this body or the body moves in a static fluid, in either of these two cases, okay, the force that the fluid would essentially exert on this body is always proportional to this c1. Okay, so this means that if I find c1, all we need, so why are we doing this, basically this exercise of stream function? We are much, all we need is to just evaluate what would be the drag force and to equate this drag force to 0 to find out the unknown velocity. Okay, so the whole exercise of finding the drag force is just limited to just finding the constant c1, and if we know c1, we can use this theorem to eventually find out what will be the drag force. So in a way, we are bypassing the steps of like calculating the velocity from the stream function, calculating the viscous stresses from the velocities, and then calculating the drag force on the viscous stresses. So it's a very tedious exercise, right? So in spite of doing all those business, it's just that you need to evaluate c1 from the far field stream function, and the fact that you know how the stream function behaves, or the fact that you know how the flow field basically behaves at far field, you know what will be the drag force on any arbitrary object, okay, which have an axis of symmetry in one particular direction. And that object just need not to be a sphere, it can be a cylinder, it can be any object. Only there are two basically needs to satisfy this theorem. The first need is that it should have an axis of symmetry. The second thing is that you must fix an axis which is coinciding with the object's center of mass. That's it. So this means that in a case where fj, which means fj, that is the drag force, if this is 0, okay, so when does the drag force become 0? It is only possible when the external force is being balanced by the drag force. Okay, in that case you can eventually find out with what velocity the fluid would move, and this is essentially the exercise of our problem. I'll stop here for some time. Did you understand what I said or not? All right, if you understood this, if you understood this, so what now we need to do is we will use this theorem, and if you now solve for c1, basically So all you need to do is, you just need to evaluate C1, and for that you need to solve this one, 4a, 4b, 4c, and 4d. And I have done that. So basically your C1, okay, will come out to be, so your C1 will come out to be 3 by 2, 1 minus u minus 1. That's it. You just solve that four equations, and you can solve, of course, by solving you will see that C1 essentially comes out this. You can do it in your place, and you can verify this result. So this means that now the drag force Fd, or we will write it as Fz, because this is the drag force in the direction of axis of symmetry. This is 4 pi, mu is basically a viscosity, the characteristic velocity uc times lc, okay, which is the length scale, times c1, and c1 is nothing but 3 by 2, 1 minus of u minus 1. Okay, so this is typically the drag force. This is typically the drag force that this is the drag force that the particle experiences, or I would say that the sphere experiences. Okay. Now, how do we calculate u, which is, so remember this u is an unknown, right? It's the particle velocity. And I say that under an only special circumstances, which I call is that the net force free condition, which means that the external force balances the drag force, or the net force on the particle is zero, will give us u, which means that if I now, if I now equate this fz, if I now equate this fz to 0, this will just give us that 3 by 2 into u, 3 by 2 into 1 minus of u is basically equal to 1, which means what? Which means that is u is what? It is 1 minus 2/3 basically. And this u would basically, so I think this is fine. This will go that side, yeah. So 1 minus 2/3 is what? So it's just 1 by 3. So that's it. So this is basically the non-dimensional velocity, okay, with which the sphere would move, by enforcing the fact that the net force on the sphere is basically zero. Okay. However, if someone asks that if I now want to hold the sphere stationary, how much force do we need to apply? Then this is actually the force that you need to apply. Okay. Now this is obvious, right? Because if you want to hold this stationary, okay, then this becomes that this u is basically equal to 0, and in the presence of a parabolic flow, if this is 0, this much amount of force is something that you need to apply. Okay. So up to this, is this clear or not? So can you tell me by by like what you understood in the theory classes, that instead of a parabolic flow, now if there is an uniform flow, and I am holding the sphere stationary, which means that this u is 0 basically. Okay, then can you tell me what was the value of C1 that you guys got? Can you, it's just that you need to apply some common sense here, and then you can answer this question. See, there is a very infamous expression of Stokes drag, okay, that what would be the drag on a sphere if there is a uniform flow coming from far field. Okay, and that thing you can just answer it from here. Can you tell me what would be the value of C1 if you want to hold the sphere? Remember, you are holding a sphere. Now the sphere is not moving. This means that the sphere would indeed now experience a drag. Okay, and what would be the value of C1, and what actually is the drag force? Can you tell me? Or do you remember, like,
C1 will be 1.
actually C1 would be 3 by 2, because the drag force was 6 pi mu UCLC, if you remember.
That is pressure plus viscous drag both.
No, I mean, see, pressure is already embedded in this calculation. Okay, it's not that pressure is not pressure is not playing a role here. So the Stokes drag is 6, so it's 6 pi mu UCLC, right? If I am not wrong, the Stokes drag.
Yes,
What
yes.
is
Then C1 will be
3 by 2, I
okay.
think.
Correct, correct. 3
Yeah,
by 2.
so what you can do is, at your home, you can follow the same procedure what we did basically. Just that your calculation will be simplified. You now need to take an uniform flow. Okay, uniform flow means your flow, that your velocity field, that is u infinity, would just be u times Ez. Okay, do this, calculate psi infinity, then calculate what modes will be present, and from that just evaluate C1. Now what you need to do is, after doing all those things, if you want to hold the sphere stationary, just equate u to be equal to 0. I think you will get C1 to be of the form something like 3 by 2 plus and minus of u, and then equate u to be equal to 0, which means, so what does it mean? This means that you are holding, if you are holding the sphere and you are applying, and you are like applying an external flow which is having a velocity, which is having an uniform velocity, okay, then the drag force, which is nothing but 6 pi mu UCLC. That's the thing. Where UC is the characteristic velocity, you can choose any characteristic velocity as you want, and LC is nothing but the length scale of the problem. For instance, you can choose the radius A to be the length scale, and so on and so forth. So you can do that, and this will be again a very good exercise of your understanding, like what you develop. All right. So we will not. So we are left with many more topics. So we will not extend this much. But without writing anything, I would just say that if you do not use this theorem, okay, if you don't use this theorem, then how will you calculate the drag force? Like, let's say you don't have this theorem with you. So then can you tell me what do you need to do? I already said the answer, but like, can you tell me? So after finding this C1 D1 C1 D1 C3 D3, what will you have? So you will have the complete knowledge of the stream function basically. So you'll have the complete knowledge of this stream function. So can you tell me
Yeah,
what you need to do? Yeah, yeah.
we'll compute viscous drag by the Newton's law.
Yes, Newton's law. Okay, that's correct. So yes, of course, you need to use Newton's law only, which means you need to relate the velocity with the stresses. But first of all, what you need to do is you will get psi here. Okay,
We'll
so
compute velocity by
yeah,
stream
exactly.
function.
Exactly. So you need to complete UR and U theta first. Okay, because you know psi. Then there is one more thing that is missing. Remember, we eliminated pressure from the stream function by taking a curl. Okay, so you need to use the equation of UR. So you need to use the R momentum equation, substitute the value of UR and U theta, and then calculate pressure.
Mm-hmm.
Okay,
Yes.
okay, because since psi is known, you know u r u theta. Now from this knowledge, you need to calculate pressure. How will you calculate pressure? That is from the R momentum equation. So once pressure u r u theta is known, you also need to calculate the viscous stresses. Okay. So the viscous stresses you will get from the knowledge of u r and u theta, because pressure does not contribute to the viscous stresses. Okay, but the drag force is not just associated with the viscous stresses. Okay, it is also, so it's associated with the total stress, which means the total stress field is what? It is just pressure times this plus tau. This is the total stress, right? I think you will be aware of that. Okay, so this total stress, from this total stress, now you need to evaluate the drag force. So there is a relationship between stress and drag force. You can, of course, so from stress you need to calculate the traction vector. So traction, from the traction vector, you need to integrate the traction vector on the particle surface to get the drag force on the surface, and then you need to equate that drag force to 0. Okay, in order to calculate with what velocity the particle would move, basically. Okay, so that's the idea. And if you don't equate to 0, this means that you are essentially trying to calculate the drag force when you are holding the particle fixed in the presence of either a background flow, or in the presence of either a background parabolic flow or a background uniform flow. Okay, so that's the whole idea. But you can now appreciate how powerful this theorem is. Like, and this theorem, as I said, this theorem not only applies to just spherical objects, it applied to any objects. The condition is that it should have an axis of symmetry. Okay, and the second condition is that the center of mass should be at the point which coincide with the axis center. Okay, with this we will stop the discussion on creeping flows. And so these discussions, so this analysis of creeping flow also applied to other topics like lubrication theory and so on and so forth. We don't have time to discuss all of this, but with this I would stop here for some time, and then we will try to solve one problem in boundary layer theory, because today's class and the next class we will be dealing with boundary layer flows, and after that we will move into hydrodynamic stability. And that precisely, so hydrodynamic, so we'll study a bit of boundary layer flows, some bit of hydrodynamic stability and shear free flows, and then if we have time we will see something on turbulence, and that's all. That's what we plan to do uh, in the interactive sessions. Okay, so we'll stop here for some time. If you have doubts you can ask, or else we'll move with something which is known as, so this is known as typically the laminar boundary layer. Okay. All right. So let's get started. We don't have much time today, so we'll just try to solve one problem associated with boundary layer. Okay. So the problem is indeed very simple, and it is similar to the one that you solve for your assignment as well. So just one second. So the problem goes something like this. So there is a flat plate. Okay. So there is a flat plate basically, and there is a free stream of air that is coming with a free stream velocity u infinity. And as you know that whenever there is an obstruction that comes in the presence of an infinite flow that is coming with some velocity, then there develops a boundary layer. Okay, and typically that boundary layer depicts the viscous effects of the fluid, which is otherwise absent if you follow the inviscid theory. Okay, so that's the idea behind the development of this boundary layer. And of course, there are some exercises which tries to investigate the how this boundary layer thickness. So first of all, you must appreciate that this boundary layer thickness is not constant. It is a function of this axial direction that you saw. That it's so boundary layer thickness typically increases when you move downstream to the plate. That is a much familiar observation that you guys must have done in the theory classes. But anyways, so the bottom neck is that it's the inviscid is the viscous effects, okay, of the fluid that is responsible for this boundary layer theory, and all its associated principles and the like the results that follows. Okay, that's basically the whole idea behind the boundary layer. Is the viscous nature that depicts the development and the growth of this boundary layer, and so on and so forth. Okay, so with this, as you guys know already, I will not like go much onto the theory. So the question says is that if there develops a boundary layer, okay, whose thickness basically is nothing but delta x when you move along the x direction, and that you know, what they're asking is that you need to assume, so they're asking is that you need to assume a velocity profile inside the boundary layer of this form, okay, which is a plus b by y plus c by y square. Okay, and then if you are assuming this velocity profile, using your appropriate knowledge of the boundary condition, you just need to evaluate this ABC, and then you need to evaluate how this boundary layer thickness delta x varies with respect to x. Okay, and I'll give a hint of how do we need to evaluate that. But before that, let's quickly evaluate what these ABCs would look like. And for that, you need to you need to help me out with this. Okay, so can you tell me how do we evaluate these ABCs? Given that we know the velocity profile u that they asked us to assume is a second order profile, which is a plus b by y plus c by y square. Okay, so how do we assume this ABC? Can you like give a hint?
Boundary
Yeah, exactly.
conditions.
Boundary conditions. So how many boundary conditions do we need here?
One is at flat plate, no slip condition.
Yeah, exactly. One is no
One
slip.
is one is at the free stream at the end of
Correct.
boundary layer,
Correct. So one
and
is that at y equal to delta, u is u infinity, and the other one.
at infinity, and one is also that stress will be zero
Yeah,
at
exactly. Exactly.
shear layer, yeah, at the
Exactly.
interface,
At the interface of the like inviscid and the viscous fluid.
viscous and
Yeah,
inviscous. Yeah.
exactly. So you are absolutely right, which means that we'll just straight away proceed with it. So what we will do it at y equal to 0, the first condition says that u at y equal to 0 is 0, and this is nothing but the no slip boundary condition. This is nothing but the no slip boundary condition, which means that if we apply this boundary condition, so u is basically 0, and this means a and all other will just turn out to be 0, which means your a eventually comes out to be equals to 0. Okay. The second condition, as you said, is that at y equal to delta, your u is basically u infinity. And if we apply this, so what do we get? So you get that u infinity is nothing but d delta plus C delta squared. But we need to evaluate one more boundary condition. The third boundary condition is what? Is it says that u is not u. It basically del u by del y is 0 at y equal to delta, which means if you evaluate del u by del y, you will get b plus of what? 2c 2c delta. This is equal to 0, which means what? So hold on. Yeah, which means what? You get b to be equal to minus of 2c delta. Okay, and then if you substitute this b here, okay, then you will get c. So what do we get? So this means u infinity is, so b is minus 2c delta, so this becomes minus 2c delta squared, plus there is also this c delta squared, which means I have u infinity equal to uh, so it would be minus c delta squared, which means your c is nothing but minus u infinity by delta squared. Okay. So if c is this, then you can evaluate this b. Your b is nothing but minus of 2 delta times c, and your c is nothing but minus u infinity by delta squared, which means your b eventually come out to be 2 u infinity by delta. So this means you have now evaluated your constants a, which is 0, b is 2 u infinity by delta, and c is nothing but what? It is c is what? C is nothing but minus u infinity by delta square. So that's it. So you have evaluated. So if you are assuming a second order velocity profile, if you have evaluated all the constants. Okay, so this means your velocity profile, how will it look like? So it will look like some u by u infinity equal to a was 0, b was basically 2 u infinity by delta. I brought all the u infinities to the denominator, so it will become 2 times y by delta, okay, minus y by delta squared. I hope the math is clear to you. Okay. You have done this many a time, so we will not spend much time on this. All right. So this means you know the velocity profile now. This is your velocity profile. So can you tell me one thing? Is u just a function of y, or u is also a function of some other things? Can you tell me? All I am asking is this is correct or this is correct?
It's
No.
a function of y as well as delta. So B
Yeah.
option should be correct.
Yeah, exactly. That's what I was
And
trying to
delta
say.
is
See,
function of
yeah,
x.
exactly. And delta is indirectly a function of x, which means actually your u is a function of x and y. So in this spirit, before moving forward, if you remember your boundary layer equations, your simplified boundary layer equations by doing all the assumptions and so on and so forth, your simplified boundary layer equations basically become something like it is del square u by del x squared plus del squared u by del y squared. Okay, your pressure gradient term was 0, and I think there was no body forces, so this basically equal to 0. If you remember, this was your boundary layer equations. Okay, all right. So that's why this suggests that. So do we have some other terms here? So I think the inertia would basically drop out. I think this is correct. Yeah. So this is correct, right? So, do we have any other terms in the simplified boundary layer equation? So, del square u by del y squared, del square u by del x squared equal to 0. Pressure gradient, you don't have the pressure gradient in the presence of a flat plate. And there is no.
Convective yeah,
Do you have the convective terms? Which, oh, okay, let's see. So, do you have these terms? So, u times del u by del x. Yeah, I think u times del u by del y. Yeah, you should have these terms as well. I don't see. Uh, Yeah, of course. I think you should have these terms basically as well. But anyways, the main reason, so the idea I was trying to say is that u is just not so u is not solely a function of y. It is also a function of x, and that's why when I think you guys have seen the lecture series on Blassius solution, that's why when you derive the Blassius solution, you don't. That means you don't treat the boundary layer equations as an ODE. It's a PDE basically, and that's why Blassius invented that self-similarity approach where you take a similarity variable eta, which is both a function of y and x, and then you would try to solve that using the similarity variable approach, okay, and end up getting the Blassius solution. All right. Nevertheless, uh, as we move ahead, so the second part, what they are asking us the second part, what they're asking us is to evaluate this delta x. Okay, they're asking us to evaluate this delta x. So where delta is basically your boundary layer thickness. So how do you do that? Can you suggest an approach? You remember, you cannot use the Blassius solution. Okay, that Blassius solution is, there is no point using the Blassius solution because we already derived the velocity profile, and then you said that your delta by x is 5 by under root of rex. Then what's the point of deriving the velocity profile? Okay, we know Blassius solution is the exact solution, but there is also one more approach which you guys also might have known, and we will use that approach to eventually find out what will be the boundary layer thickness. Can you suggest me that?
In course was that momentum integral.
Yeah, exactly. You need to use that momentum integral. So I will not derive this, but I'll, as you have said, the infamous momentum integral equation for a flat plate. So the momentum integral equation for a flat plate is basically something like this. It is tau w by rho u infinity squared, and this is equal to d theta by dx, where your theta, as you guys know, is known as the momentum thickness. Okay, this theta is your momentum thickness. All right, so I guess you guys will be familiar with this equation, but because this is the ultimate output of the momentum integral approach. Okay, so I'll just hint you how to do this momentum integral approach. So all you need to do is you need to take the boundary layer equations, integrate those boundary layer equations from 0 to delta, and then when you integrate that, you remove the y dependency, and you just end up getting this momentum integral equation basically, which gives you how the momentum thickness varies along as you move downstream to the plane. Okay, so we will use this, but before that we need to evaluate, as you can see, this tau infinity. And remember, here we will just follow a non-dimensional approach. So we'll follow a dimensional approach only because these equations are not that tedious. So we will use this rho and all those things. We will just follow. So here all the variables are dimensional in nature, and don't confuse that with the other things that we did in the previous classes. Okay. So for that, let's now first evaluate tau w. So tau w, as you guys know, tau w is what? Tau w is nothing but mu times del u by del y, and this is evaluated at y equal to 0, which is nothing but the wall shear stress. And if you do this, your tau w will just come out to be 2 times u infinity mu by delta basically. Okay, so this means we know how. So of course you can just check it out that if you know your u, just you need to evaluate what this should be, del u by del y at y equal to 0. That's it. And this means that it will be what? It will be minus of 2y by delta squared, and that's what you exactly wrote here. Okay. All right. Okay. So now if you know tau w, we will directly use this momentum integral equation, which means what? Which means we have this 2 u infinity mu by delta times rho u infinity squared. Okay, and I think you guys know that you can also express your momentum integral in terms of the velocity profile as something like this. Sorry, not momentum integral, the momentum thickness as something like it is integration. So theta can be written as integration 0 to delta u by u infinity. It is 1 minus of u by u infinity. And I think you know this. Okay, so I think you know there is something also known as displacement thickness. We write it as delta star, and there is also something which is known as delta star by theta. Can you tell me what is this term called? Delta star by theta.
Shape factor.
Yeah, exactly. That was one of your questions in the assignment. Okay. But nevertheless, uh, so I was trying to say that delta star, which is the displacement thickness, is nothing but something like this. It is integration 0 to delta 1 minus a vy u infinity uh, by dy. Okay. Yeah. So the thing is that you now need to evaluate this bit. Okay. So let's do this. But before that, let's just simplify this term. This should be u infinity, and one in u infinity would cancel. And what do we have? Do we have something else? So okay. And what we will do is we will write this mu by rho. We will write it as just nu. So we just end up having 2 times nu by delta into u infinity. And this is just d dx of integral 0 to delta. Okay. U by u infinity, you know, u by infinity is what? It is 2 times y by delta minus y by delta squared, y by delta minus y by delta squared. And then you have this term, and you have just 1 minus of this term, which is 1 minus 2 times y by delta plus y by delta squared and dy. Okay. All right. So now there is an easy way. So as you can see, all you need to do is you need to do this integration. Okay. So there is an easy way of doing this integration. What you can do is you can take y by delta as m. Okay. Which means your dy would be just delta times dm, because delta is just, see, your delta is not a function of y, which means any variation on y will not affect delta. Okay, and that's why you can write dy is just delta times dm. So this means your integration eventually simplifies to what? So and also you can see at y equal to 0, your m becomes equal to 0. At y equal to delta, your m becomes equal to 1. So this whole integration will just reduce to what? It will just reduce to integral 0 to 1. It is 2m minus m squared. Okay, okay. And this would be 1 minus 2 times m plus m squared times dy is just delta times dm, but we can remove the delta out of the integral because, as I have said, the delta doesn't have any variation along y. So all you need to do is just evaluate this. Okay, and this is just a simple integration, and I have done this a priori, so I'll just write down the result in the interest of time. So I have just done this just comes out to be 2 by 15. Okay, which means that your whole part, that this part essentially simplifies to d delta by dx times 2 by 15. Okay, it's that easy basically. Yeah, which means what? Which means that I have 2 nu times delta by u infinity simplifies to just 2 by 15 times d delta by dx. All right. Okay, so what next? So how do we evaluate delta from here? It just no, so it's not that simple integration, right? Because you cannot directly integrate this because you have a delta here. Okay. So how do we do this? Can you give a hint?
We'll take delta right side.
Yeah. Okay, let's do that. Let's take this 2 delta times t delta. Okay, and let's bring the all other things here, which means 2 times 15 times of mu by u infinity times dx. Okay, what then? This is still not integrable, right? Because we have a delta d delta here. What do we do now? So you cannot integrate this, right? Directly. Because there is this delta d delta. But here is the trick, okay, that you guys need to take care of. So you can write the term on the left hand side as something like d of delta squared. Can you write this or not?
Yeah.
Exactly. And this becomes 30 nu u infinity dx. Now this is integrable because this is also a differential. This 30 nu by infinity is a constant, and this is also a differential. Okay, which means you can now integrate this. Okay, so if you integrate this, you will get what? You will get delta squared, and this is equal to, yeah, let's not do a indirect integration, let's do a direct integration. So what do we have? At x equal to 0, I know that my boundary layer thickness is 0, and at x equal to some x, I know that my boundary layer thickness would be some delta of x, which means I have delta squared equal to 30 nu by u infinity x, and if you apply the limit, we'll see that it eventually comes out to be something like this. And this means that your delta is nothing but square root of 30 nu x, okay, by u infinity. See, this again gives us a very important conclusion that your boundary layer thickness indeed varies as square root of x, as you guys have seen it multiple times in the Blasius solution as well. Okay, and so there is something which is known as the scaling analysis, and from the scaling analysis also, see, scaling analysis is very simple. We have done non-dimensionalization multiple times. In the same speed, if you non-dimensionalize the boundary layer equations, okay, you can eventually show that your boundary layer thickness basically varies as square root of x, and indeed it's also preserved here. Okay, all right. So this is the answer that we are looking for. Okay, they are just asking us how does delta basically varies with x. So delta basically varies as something like this. But let's do one more trick here, and we will see like what we can do. So what I will do is, let's do one thing. Okay, so this is 30 nu x by u infinity. Let's divide and multiply by x on both sides. Okay. So then what do we get? So I can write this as root over 30. How can I write this? Basically, I can write this as root over 30. Hold on. Okay, let's write this as root over 30 times root over x square, which will be x, and then I can write this as something like this. I can write this as nu times u infinity x. So I think the math is correct. So just let me check. So these two x I'll bring it outside, and I'll just take these two terms inside the square root. Okay, and that is correct. This is just nu by, yes, or it's wrong. Okay, so is this correct or is some mistake that we did? So your delta is basically this 30 nu x by this. Then we have multiplied and divide the denominator by x on both sides. Okay. And then,
Root 30 x by root RE.
yeah, exactly, root 30 x by root 30. But I think, so, hold on.
Mu we can write.
Yes. So I think this, we can write this something like this, right? I can write this as u infinity x by nu. This is fine, right? This is fine.
Yes.
Yeah. And then this becomes, yeah. And then this becomes, as you have said, this becomes square root of REX. Okay. Which means I can now write delta as square root of 30x by square root of REX, which means I can write delta by x, that is equal to what? Square root of 30 by square root of REX. Okay. Now, if we evaluate this square root of 30, if you evaluate this square root of 30, okay, you will see that this square root of 30 come out to be 5.48, and this is square root of 30x, which means this is typically how your boundary layer thickness essentially varies. That is something that we have already established. But in addition to it, you can see the closeness with which it is related to the Blasius solution. Okay, so if you remember, Blasius solution was delta by x is 5 by rex, right? Which means if the the approach that Lassius follows using the similarity principle and then finding out the constant c which came out to be equal to 5. If you follow the momentum integral approach, okay, and then consider a second order profile, okay, of the form that we already saw, your answer is very much close to the Lassius solution. and and what is the error? Basically, the error is 5 minus 5.48, or the other way around, 5.48 minus 5 divided by 5. Okay, this will be the absolute error, and you can calculate this and multiply with 100 to get the percentage. And you can see that the error will be very less. Okay, which means the momentum integral approach actually works. That's what I was trying to say. Okay, and then choosing the second order profile also helps. And your result, which is basically how the boundary layer thickness varies with x, this is also very it's very close to the exact result predicted by Blasius. Okay, that's the idea. That's the idea that I want to convey with this. With this, I will stop here for today. Uh, so if you have any questions, you can put forward, or else in the next class the plan is to do some more sums. We will try to understand. So we'll try to do one sum related to the Blasius solution and something like the Faulkner scan wave solution and things like that. If possible, we'll do that. And then once this boundary layer theory is finished, we will look into something which is known as hydrodynamic stability, and that's a very important concept. And this is typically important in the sense that it's one of the I would say it's one of the primary topics of fluid dynamics research. So that's why this topic is important, the hydrodynamic stability. So we will try to understand this hydrodynamic stability. There is something which is called as the Orr-Sommerfeld equation, the Rayleigh stability equation, and so on and so forth. We'll try to understand those equations. And once we are done, so hydrodynamic stability might require one or two classes. So once we are done with that, we will, if time permits, we will see some bits of turbulence, and then we will finish up. We'll just browse through what we have learned from week 1 to week 12, let's say, and then we will finish the interactions. Okay, so that's the plan for the next subsequent classes. But now, if you have any questions, you can ask me, or we will call it a day for today. Thank you guys for attending. Feel free to ask your doubts in the discussion forum, or if you have any doubts in one of their assignments or the answers are not correct, just feel free to write it in the discussion forum, and we will come back to you with the solutions. All right. If you have any doubts, you can ask, or else we will stop here uh, for today. Okay, so if you don't have any doubts, thank you for attending. I'll close the meeting now. Thank you guys once again. So I'm ending the meeting.